This project detailed the design and implementation of a sequence shift add multiplier circuit using Model C for simulation and Quartus for synthesis and hardware implementation. The design multiplied 2 4-byte unsigned number to produce an 8-byte result, employing a sequential multiplication algorithm. The circuit incorporation a start signal to initial multiplication process and a done signal to indicate completion. The report will cover algorithm modeling, RTL design, data part unit, control unit, top level, and design verification of the circuit. The focus will be on design a multiplier, the multiplies 2 4-byte unsigned number. Apply the sequential and start the signal, loaded the number and complete the signal.
Assalamualaikum and hello everyone. My name is Siti Nuradiba binti Muhammad Kamil. My number matric 231373667. Today I will explain the algorithmic modeling of a sequential shift add multiplier, which is used to multiply two unsigned 4-bit numbers. This method efficiently performs multiplication using the addition and shifting operation. Let's start with the algorithm. The process follows these key steps. First, initialization. We set the product to 0 and initialize a counter to track integration. Second, loop execution for n-bit multiplication, n equal 4 in our case. We check the less significant bit, LSB, of the multiplier. If the LSB is 1, we add the multiplicand to the product. Then shift the multiplicand left and shift the multiplier right to process the next bit. Finally, we increment the counter and repeat the process until all bits are processed. Last, termination. Once the counter reaches n, the final product is stored in the register and written. Now, let's look at the flowchart. This visual representation helps us understand how the algorithm works step by step. The process starts by initialize register C, A, M, Q and count. A decision block check if Q0 LSB of the multiplier is 1. If yes, we add the multiplicand to register A. If no, we skip the addition step. Next, we perform a shift operation. The multiplier Q is shifted to right and the multiplicand M is shifted to left. The counter decreases and we repeat until the reach 0. The final product is stored in the register A and Q.
Hi, my name is Rana Charia and I will do the explanation about RTL modeling. There are two states here, S0 and S1. In S0, start, load multiplicand and multiplier, initialize the product register to 0. If the reset is activated, stay in S0. Next, S1 or state 1. If the least significant bit of the multiplier is 1, add the multiplicand to the product. Shift the multiplicand to the left and shift multiplier to the right. Okay, in done, If the count reaches the bit width, transition to S0. Otherwise, repeat S1.
Assalamualaikum and have a good day. My name is Nur Amira Elina binti Saidin and my metric number is 221373165. I will be presenting a Verilog implementation of both multiplication algorithm, specifically for an 8-bit size multiplication. The module we designed is called MPDU, and it performs an 8-bit multiplication using both methods. It takes 2-bit inputs. It takes two 8-bit inputs, a multiplicand and a multiplier, and produces a 16-bit product. The operation is performed in 8 clock cycles, and a John signal indicates when the multiplication is complete. The module consists of several key registers, which is A stands for accumulator. It stores intermediate result. The next key is Q, which is multiplier register, stores the multiplier. M, multiplicand register, stores the multiplicand. Next key is Q1 for extra bit. It used for both shifting process. Count for 4-bit counter. It keeps track of the number of iterations. The multiplication process follows this step. On reset, all registers are set to 0. When start is triggered, the multiplier and multiplicand are loaded into Q and M. If the least significant bit of Q is 1, we add M to A. Perform an arithmetic right shift on A, Q, and Q1. It repeats for 8 cycles. After 8 iterations, the product is stored in A and Q, and the John signal is set to 1. For the correction and improvements, initially, there were some issues with blocking assignment, equal instead of non-blocking assignments, less than equal. Also, the shift operation and counter decrement were not correctly implemented. These were fixed to ensure proper sequential execution. In summary, this Verilog module efficiently implements 8-bit sign multiplication using both algorithms. It ensures accurate result within a fixed number of clock cycles. This method is widely used in digital systems, including arithmetic logic units (ALUs) and DSP processors. We move to the next slide. Next, let's move to the waveform analysis of a tensor simulation for a digital multiplier unit. We will go through the signals timing analysis and conclude with the verification of functionality. Let's begin with the key signals involved in the simulation. First one is clock. This drives the entire system, ensuring synchronization. Next key is reset, which is initially low, indicating it is inactive at the start. For the key start, also low at the beginning, meaning the multiplication process hasn't started yet. For the key multi, the binary value, which is 0000, 1101, which is equivalent to decimal 13. For the key multi, which is the binary value is 00001011, representing decimal 11. For the key product, it is initially set to all 0, but after the computation, it updates to 100111111, which is equal to 143 in decimal. The key tone is activated to indicate the multiplication process has successfully completed. Now, let's look at the timing behavior. The product signals remain at 0 initially and only updates when the computation completes. The done signal confirms when the multiplication is finished, ensuring that this result is available at the expected time. To summarize this presentation, the multiplication unit correctly computes 13 multiplied by 11, which equal to 143. The waveform results confirm the expected functionality and proper timing of the digital multiplier. Let's conclude my presentation. Next, let's move to the waveform analysis.
My name is Fang Jianwen, number matric 221373138. My part is control unit. The MPCU module is a control unit for a multiplier, managing operation like loading, shifting, and adding. It ensures proper sequence of multiplication step using a finite state machine. The finite state machine diagram displays a state transition diagram showing S0 waiting for the start signal and load data, S1 multiply state, perform addition and shifting unit done, state register and initialization, present state and next state store the FSM state, use two states S0 and S1, state transition logic, reset to S0 when reset is 1, transition on the negative clock edge, next state logic, transition to S1 when start is 1, transition back to S0 when done is 1. Output logic is S0 load is 1 if start is 1, load initial data. In S1, it perform add and shift until done is 1. I will explain the simulation waveform of our control unit. The first signal is the clock, which continually toggle and adjust all operations in the control unit. Reset and start signal. The reset signal is low, meaning the system is not in a reset state. The start signal also remains low, indicating that no new operation has been initiated. Done signal. The done signal stays at 0, meaning the control unit has not completed its operation yet. Control signal load, shift and add. Initially, all control signal load, shift and add are is state 0 around 40 nanoseconds. The shift signal change indicating a shift operation. Later around 7 nanoseconds, the add signal transition, meaning an addition operation is taking place. This waveform shows the correct sequence of control unit operation. First idea, that shift followed by addition. However, say the start signal but was not triggered, the done signal remains low. The next part is I will be explaining my Verilog module top level, which implement an 8-bit multiply using a control unit and a data unit. The module takes two 8-bit input, multi-C and multi-L, multiplus them and produce a 16-bit output called product. It also has control signals like start, done, clock, and reset for operation management. The multiplication process is controlled by two submodules and control unit. It generates control signal to manage operation like loading, shift, and adding. Data unit, it performs the actual multiplication using a shift and add method and store the result in the product register. When the start signal is received, the control unit initiates the multiplication. The data unit load the input into register. The multiplication is done using shift and add operation. Once complete, the final product is stored and the done signal is set high to increase the operation is finished. This design effectively multiply two numbers using a hardware-based approach. It a modular, making it easy to modify or explain. Next, I will explain the simulation waveform of a simple multiplier circuit. First, let's look at the clock signal. This is the simple clock which synchronizes all operation. It continually toggle between high and low state. The reset signal or reset is set to 0, meaning the circuit is active and not in a reset state. Next, we have two input signals, multi-C and multi-L. They represent the number we want to multiply. Here, multi-C hold the binary value 0000101, which is decimal 5, and multi-L hold 0000011, which is decimal 3. At the state, the product signal will store the multiplication result is initially 0. As the operation progresses, we see the product value change to 1111, which is decimal 15, the correct result of 5 times 3. Finally, the done signal transition to indicate that the multiplication is complete. This waveform confirms that the multiplier circuit is functioning correctly, the input are correctly processed, and the exponential output is generated. Thank you.
This report successfully demonstrates the design and synthesis of a function sequence shift add multiplier using model sim and quarters. The simulation result in model sim validate the correctness of the RTL design. Design verification of the circuit confirming its ability to perform multiplication according to the specified algorithm. The synthesis process in quarters successfully mapped the design onto a target FPGA. The project successfully integrated the data part and control unit, showing casing effectively use of sequence and sequential logic to implement the shift and add algorithm. Further work could explore optimization to increase throughput or the investigation of alternative multiplier architecture for performance comparisons. The complete design serves as a practical example of digital circuit design, highlighting the importance of simulation and synthesis tools in verifying and implementing digital systems.